Welcome back, everybody. This is my 50th video, and man, oh man, am I excited because we're talking about the dreaded monad. And I'm excited to explain this to you. I think this should be the most thorough, clearest definition that I've seen on YouTube because I'm going to approach it a lot of different ways. So I'm going to include code examples, also include the category theory, the different type declarations, those sorts of things, so that you get a broad perspective on it. And if one example or explanation doesn't click, hopefully the next one will. So first thing that I think a lot of people skip when explaining monads is, why do we need monads and what do they do for us? Well, as I've said here, monads solve problems by providing context for the data. For example, promises from ES6 or that shouldn't be 2017, 2015 are monadic. So they are a type of monad. They behave like a monad. Their implementation is a little different, which is why they are just monadic. But they provide a context for the data so that the return value from a promise the promise itself, I should say, can either be pending, fulfilled with a return value, or rejected with a reason. This gives unpredictable data, for example, asynchronous values that can fail, predictable behavior, and restores composition. And we do this by chaining. So we can create the promise chain. And this allows us to avoid callback hell. And that was the problem that promises allowed us to solve. Instead of having to pass callbacks into every function, we were able to once again compose, just like we can with synchronous code, our asynchronous code together. And this is done through the monad pattern. And the monad pattern, again, provides context for the data. The context in the case of an asynchronous call wrapped in a promise is the state, and then either the data or the reason it was rejected. So there's that extra piece. It's not just if you called an API that was going to give you the local temperature, it's not just the temperature, it's also whatever data comes with that temperature. So the fact that it was a fulfilled promise, which allows us to give us consistent behavior so that we know we can call .then on it. And if it's rejected, we know that we can call .catch. And this allows us to access the data from inside the promise. And so these are the special functions that allow us to get the data out of the monad. And then we can transform the data once we've got the data out of the monad, and then put it back into the monad. So for example, if you return from .then, it puts it back into a promise. And then you can chain again, which is how we restore composition. So that's that's why we use monads to provide, because if we just asked for the return value of an asynchronous function, we're just going to get undefined because that's the default value, and that doesn't do any good. We needed to fix this problem. And so callbacks were used, but callbacks didn't have compositionality. Monads, in the form of promises, gave us compositionality. So that's why we need them. Now, that's great. If that makes sense to you, awesome. If not, fear not, we are moving on to functors. And we're taking this one step at a time. So, first of all, what are functors? Well, just like monads, functors provide context for our data. And so if we, for example, had the numbers 1, 2, 3, 4, 5, and we wanted to add 1 to every single one of them. Well, what we could do is we could do something like let new 1 equal add 1. I've defined it down here, so I obviously have to move it up, but add 1, 1. And then let new 2 equal add 1, 2. And we could do that to every single one. But these values share something, right? They are similar in some way. We know, for example, by looking at them, that they are all numbers. And so they share similar characteristics. They can be passed into the same functions, any function that's expecting a number. And so if we group them together into a single piece of data, then we can perform operations on them that will all behave by similar rules. And so that's what arrays allow us to do. And by definition, functors are anything that can be mapped. In JavaScript, the easiest example of that is an array because it has an actual .map function. I have created a new map just for consistency across all my examples because I will be passing the values into a function. So it's clearer if I'm able to pass them into a curried map function. Excuse me. But we can see that what it provides us is one piece of data called nums. And it has multiple values inside of it, but we know how those values relate to each other. For example, the array is indexed at 0, and we know that we can iterate through it one at a time, and it's in order. And as long as we get those values out and we're following some standard rules, which means that we don't mix data types inside our list, then we can treat them all the same way. And so what map allows us to do is take our functor, which is our array of values, pull out each value individually, and pass it into a function that works at the level of values. So as I said, add1 expects a number. It doesn't expect a functor, so it doesn't expect an array of numbers. It expects a number. And so we need a bridge that goes from our functor to our function. And that bridge is our map. So this type signature here says that we need to give map a function that goes from A to B, so type A to type B. So that'll be a number to a new number. And then we need to give it a functor over A's. And in this case, our functor is an array, and our A's are numbers. So we have an array. The F is an array of A's, numbers. And then by applying the A to B function to each value in the functor, we take the value in the functor from A to a value of B, and then map says I will also return a new functor of the same type with the transformed values. And as we know, if we call .map on a array, we get a new array of the same length with the new transformed values. So if I have map down here, I pass in add1, I pass in nums, it's going to transform each value in the nums array and give me a new array. And there we go, each number has been incremented. So to summarize, a functor is something that can be mapped. Our functor, in this case, is an array, and the array is the context for the data. It says these different values are related in some way. And we know, based on how map behaves, that we are able to access those values and stay within that context, because what we get back is a new functor of the same length. And that way, we can compose. We can call .map, 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 or we could pass in result1 to be result2, for example. I don't know if I've already declared a result2, so I'll call it 12, just so I know I don't have one of those. And I could do add1, I could pass in result1. 12. And just like with, as I mentioned at the beginning, just like chaining or composing promises, we can compose or chain our mapping transformations. So map for functors is a bridge between functors over A's to functions that work at the level of values. Now, what if we wanted to map a functor over another functor? Well, that would be called applicative functors. So applicative functors are no longer dealing with a single functor. They now have two functors. And so we want to, let's say, apply add together to these two functors, an array of 1 and 2, and an array of 1 through 5. Well, we want to add the 1 to the 1, the 1 to the 2, to the 3, to the 4, to the 5, the 2 to the 1, to the 2, to the 3, to the 4, to the 5. We understand how that works But we can't just .map or call map on 1 and 2 because our map function only deals with one functor. And it deals with functions that deal at the level of values. So we have to make a new functor or a new map specifically for applicative functors. Well, what the heck is an applicative functor? You've just said that we have 2 functors. Well, we can't actually apply 1-to-1 because we haven't said what to do with it. And so what we can do instead is have a function like add together, which takes 2 parameters. And we can say, all right, the value from the first value we're going to get is going to be from the first functor. The second value will be from the second functor. So all we have to do is partially apply add together to each value in the first functor. And as a result, we'll get something that looks like this. So we now have a functor of functions, or an array of partially applied functions. And so we have the add together function where x has become 1 in this first one, and we're still waiting for a y. And once we have a y, we'll get a value. And then we have the second function where add together is partially applied. X has become the 2, and we are waiting for the y, which will be from the second functor. And now we have values in a functor that can be applied to a functor. But again, we can't just map over it, because if we just take these functors out, or these functions out, that's not going to work quite right, because we need to apply a single transformation to a functor, not multiple transformations across a functor to another functor. And so I've created this app map, which is just an applicative map for, or a map function for applicative functors. And so, as the type signature says, what I just explained, a functor of a's to b's, so an array of functions that go from a to b, and then a functor of a's, so a function of an array of untransformed numbers to an array of transformed numbers. You can look at the code if you would like to fully understand it. It's not super complicated. We take the second functor, we map over it to get the values, and we reduce the first functor across those values so that we can get a new set of values by applying the applicative functor, this guy here, to the functor. And so if you look down here, to get the result, I'm going to pass the applicative functor, the partially applied functions, to appmap as my functor of transformations, and then I'm going to pass in my functor of 1 through 5. If I run this, I need to save it first. There we go. Now we get our new transformation where we've applied 1-to-1, 2-to-1, 1-to-2, or 2, and well, we've applied 1 to each value and we've applied 2 to each value, is what I'm trying to say. I think that's fairly clear without me stumbling over my explanation of it. And so why does this matter? Well, because we've gone from applying a function that works the level of values and returns a new value to a functor, to actually applying the values in a functor to the values in another functor by using a function that accepts values and returns values. The only difference now to go from applicative functors to monads, if you understand everything up to this point, we are awesome. We are in good shape. Because all we have to say is instead of taking values and returning values, we need to take values and return values in context. So remember how I said that the array in this case is the context? And then when we returned it, we got our new values inside that same context because we mapped. That's the same thing that we are going to do with our monad, is we are going to accept values out of the monad and then transform the values and put them back into a new version of the monad with the context kept, because the monad is the context. So let's move down here. I have made what I will call the first monad. Obviously, it's a bit of a play on words, but I have made it hopefully as simple as possible. So we have a function called pure, and all it does is take a value, x, and stick it in the monad. Well, what is the monad? It is simply an object with a property called first, and that property first points to the value. As I said, monads solve problems for us. This solves no problems. This is just to show you how a monad works. So don't try to figure out my evil scheme behind this. This is just to show you that monads are simple if you understand everything up to this point. Because if we look at the function signature, we now have a map for monads. And it takes a m of a, which means a monad containing a value of a function that returns, or a function that takes an a and returns a monad containing the transformed type of b. And then it returns a monad of type b. This should look very similar to what we just saw, because we are taking a value, we are taking a value that's wrapped in something. If I were to change this, for example, to an f, we know what an f of a is. That's just a list of a's, for example, a functor of a's. And then if we return that into a function, if we have a function that returns a function that deals with a's to b's, and then returns an f of b, that's what we just saw, right? We were dealing with values in a functor, so like a list, transforming them and returning a new list. That's what we started with. But now we are taking values that are in a monad, and instead of just returning the transformed values and sticking them back into a functor, we are going to transform the values, stick them back into the monad, and then return the new monad with the transformed values. So how do we do that? It's pretty straightforward in this example. We just look at the first property in the monad and pass it into the function that we give it. Now, it's important that, like I said, the function does not take values and return values. It takes values, transforms them, and puts them back into the monad. So the pure function up here takes a value and puts it back into the monad. So if I give times 10 to my monad map as my transformation function, it's going to take the first property, which will be 10, out of the monad. It's going to feed it into times 10. So at that point, it's just a 10. And then it's times 10 is going to multiply it by 10. So we'll get 100. And then stick it back into a new monad of the same type. And so that's going to be just a object with the first property as set to 100. Oops, down a bit too far here. So if I run this, first monad result is an object with the property 100. So what happened there again was that we passed in 10 inside a monad. It got pulled out by our monad map. We fed that pulled out value into our transformation function, which was expecting a value. It transformed it and then put it back into a new monad of the same type and returned it. And now we have composition. So if I remove that and I feed the first monad result into the second monad result, which will be fed through the monad map and passed to times 10 yet again, I can then console log second monad result. And we have composition. Bada bing, bada boom. And so you might be saying, all right, Nathan, that's fine. I still don't think I really understand monads. What was the point of this? You're just dealing with objects. I thought this was functional programming. This is also pointless. Yes, I am well aware. And so, if you're not, I will show you the maybe monad. Still using objects because I want to keep this clear. Don't worry, hang in there. I'll move to a functional version in a second. But I think this is very clear. Plus, I'm adding a little bit of complexity. So let's stick with objects. We now have a new function called pure3. It's the same as pure above, except it's dealing with a different monad. Because like I said, monads have special functions that interact with them. And we have to declare those functions for each monad that we create. The monad has the same type signature each time, but the functions that interact with it, the monad map and the pure, which is what puts it into a default context, in other words, takes a value and sticks it into the monad, those need to be defined for every monad so that the monad knows, so that we know how to interact with the values in the monad. Well, I've also added a fail function, which no matter what it takes, no matter what is passed to it, it sets the state in the monad from true to false and sets the value from being the actual value that was passed in to a value of nothing. So this would be the case, maybe you were making a call to an API and it had the ability to and you had the ability to pass in a fail condition. And it's like, all right, if an error occurs, what do you want me to do? You could say, set it to fail. And that would then cause your monad state to flip from true to false and set the value automatically to nothing. Now, I have changed the name down here from monad map to bind. That's because that's the Haskell name for it. And all this is doing is checking to see what the state is in the monad. So if the state is true, then it will grab the value property, feed it into the function, and then return it. That's exactly like what we were doing above, so nothing's new there. Otherwise, it will return fail. All right? Fail called, so it'll be the actual object, state false, value nothing. We're now using a function called add42. It takes a value, adds 42 to it, and then puts it in the default context for our new maybe monad, which is going to stick the transformed value into the value property and set the state to true. All right, so let's look at it. We're passing in 10. That 10 will get pulled out of the, well, we're passing it into peer 3, so we'll have an object of state true, value 10. That's going to be checked to make sure the state is true. It will be. So we'll grab the value out, feed it into add42, which will take the 10, add 42 to it, and then stick it back into a new monad with a state of true and a value of 52. That'll then be a new monad in the same context, the same shape, so we could compose it. And there we go, state true, value 52. So like I said, we could then compose it. But what about this fail function? Well, here we have passed maybe 1, so the result, this guy here, state true, value 52. We're going to feed that into an automatic fail. I'm just going to say we passed it off to something and that called the fail function. All right? That value is going to be transformed into a state false, value nothing. We're going to then try to add 42 to it because that's the function that we passed in. But what's going to happen? Well, it'll be the bind function will check the state. The state will be false, so it will pass along fail. False, value nothing. That will be stored in maybe 2. And then maybe 2 will be passed into bind along with add42. Bind will check the state, see that it's false, so it'll call fail, which will pass along state false, value nothing. And so do you see what this looks like? This is just like promises, where once something fails, it gets passed all the way up the promise chain, and you can then handle the failure at the very end. So if I need to change this from maybe 1 to, for example, let's check maybe 2 first. State false, value nothing. And then maybe 3. State false, value nothing. So what does this do for us? This allows us to contain failure in a controlled and expected way that we're able to gracefully exit. So instead of crashing if an error occurs, we can say, no, we expected an error, just put it in this default context of having a state of false and a value of nothing. And then because bind knows how to unwrap a value from inside a function, or inside of a monad, and decide whether to pass it into the transform function or just give it a default fail context, it can just bubble all the way up through our process to the point where it just fails, no matter what. That's so useful because we don't have hard crashes at that point. And so like I said, you might be saying, all right, well, objects are fine, but I thought I heard Brian Beckman say that monads are just better functions. Well, let's look at the maybe monad as a function. So again, this is all code that I just wrote based on what I know about monads. If something doesn't seem quite right, let me know in the comments down below. But I have created a new pure function. I'm calling it pure maybe. And we are going to be using just to identify a value that has not failed. And we will call nothing, and we will create a pair of nothing with null to identify a fail condition. So again, these are just like the functions above, but instead of them being objects that are returned, they are pairs with a just and a value, or nothing and a null. I'm then going to assign pure maybe to just, so that if I pass in a value, for example, 10 to just, it will then become a pair of just 10. I'm going to pass the executed fail maybe to nothing, so that nothing becomes the pair nothing and null. I just created these helper functions, grabs the first item from the pair and returns it, grabs the second item from the pair and returns it, just for ease and clarity of function down here. And so we now have a function called add7 that takes a number and puts it into the maybe monad by calling just and a value. And by calling just and passing in the transformed value. So what does this actually look like? Well, what it will do now is instead of checking for a state property, it will just check that the first item in the pair is just, which means that the value was successful. If it was, it'll pass the second, which is the actual value, into the function. Otherwise, it will return nothing. And so now, if we go down here, what we have is maybe 4, which is just 3. So a successful value of 3 passed to add7. So add just 3 will get, or 3 will get wrapped in a just. It'll be a pair with just and 3. It'll check for just, that'll be successful. Pass it in to add7. We'll add 7 to 3, which will be 10. It'll wrap it in a just, which puts it back into a new maybe monad. And it'll go all the way through our process here, adding 7 every single time. But we still have composition. And we have just 31 at the end. And now, if we wanted to, at the very end, get our result, I guess I don't really need to go maybe result, but if we were to call bind maybe, let's do this. Call bind maybe with maybe 7 passed in, which will be our 31. Then the function that we want to apply to it could be a console log. And we get the actual value 31. Now, why don't we get the just 31? That's because at the time when I'm console logging it, we are inside the monad. That's very important to understand. It's not just 31, just like when you're inside a .then function, you are not dealing with a promise anymore. You are dealing with the value inside of the promise. We have taken the 31 out of the pair, and we are dealing with just that value. That's the value that is being passed in to our transformation function. Hopefully that is clear. If not, leave comments down below. I'd love to explain it further. Now, this is where people get, they're panicking a bunch about whether or not promises are actually monads or not, and it's because of the way that then is implemented. So the function signature for bind takes a monad of A's, or a monad over A, and takes a function that takes an A and returns a monad B and returns a monad B. Then has the exact same function signature, but it also has another function signature, which accepts a monad of A, so a promise with a value of A, and a function that takes an A and returns a B, not a monad of type B. So not a promise, not B wrapped in a promise, but just B. and then returns an M of B. So what it's doing there is it's saying, all right, you don't have to turn it back into a promise. We'll just do that automatically for you. So that then if you call .then and you just take the regular function, like add 1 from above, add 1 just took a number and returned a number, then we'll wrap it in a promise for you, and then pass it into the next then. Console log will just output that to the console, no promises involved, and .catch will just catch any errors that occur. What is the pure function, which puts it in a default context for promises? Well, that is promise.resolve. That is going to take your X and wrap it in a promise. So it will look like this. Now let's say, well, just be X, I guess, at that point. And then based on the state of that promise, then or catch knows what to do. So if it's pending, don't do anything. If it's fulfilled, .then will be called, and it will pass the value out of the promise into the add 1. Add 1 will then return a value either as a new promise or just as a value, and .then will either decide to pass that value along or unpack it, wrap it up in a new promise, and pass it along to the console log. And there we go. Our value will be 11. And that's 11, not a promise of 11, because at the point when I'm console logging, I am inside the monad. The value has been taken out of the monad, fed into console log, so it's no longer wrapped up. I console log it, and then I'm back into the monad. All right? Hopefully, that was enough variety of explanation that you understand why monads are useful, what they are for, how they restore composition. They provide context for a data, because number 10 tells us nothing about whether or not it has been received yet. And if we're dealing, for example, with asynchronous code, that's what promises solve. Promises say whether or not an attempt to get data was successful, unsuccessful, or not complete yet. For the maybe monad, it tells us whether or not a value exists or not. If we were calling an API that was supposed to return a value, we could wrap it in a just. And if we got the value, that's great. We know how to get the value out of that by checking if it's a just and then just unpacking it. If not, if it was unsuccessful, excuse me, then all we have to do is pass along the nothing value, and we can handle that because we know the shape of the nothing value. Let me know if that was clear. Let me know if it was not clear. Love to explain it further. I know there are very simple explanations. Shout out to MPJ from Fun Function. His explanation is very quick and to the point, and he simply says that monads can be flat mapped, functors can be mapped. If that makes sense to you, that's great. Hopefully my variety covered every question you might have had. Tried not to go too deep into category theory, but touch on it here and there. So let me know if this was useful. I know I've said that a few times now, but I will see you in the next video. Thanks for watching. Bye.